Thank you, Harris, for the introduction, and thank you, Jimbo, for inviting me to give a talk at this webinar. And I'm really excited to give some update on this project called Agile Co-Simulation for Cyber Energy System Security. And first, let me introduce my team. It's taking some time to. This is a collaboration of an interdisciplinary team, including power system engineers and also computer scientists and applied mathematicians as well. So myself is a power system engineer, and the co-PI of this project, Nathan Yi, is a cybersecurity expert, and we have technical advisor Philip Tao, and we also have computer scientist, aeronautist, Kendall Hunter, Ryan Mas, and Chris Lawson. For the applied mathematician team, we have Chris Vogel, Ali Fox, and we have another power system engineer, Ryan Sun, with us as well. So the funding of this project comes from multiple program offices under the Department of Energy, and also from the Environmental Security Technology Certification Program under Department of Defense. And the purpose of this project is to support the cyber physical modeling and co-simulation for a portfolio of energy system related projects at Lawrence Livermore, so that we can build up a cohesive collection of simulation building blocks to streamline the cyber physical interdependency analysis. For this talk, I will first give some introduction on the co-simulation projects that are going on at Lawrence Livermore, and I will give some in-depth introduction on 4 use cases. The first is collaborative autonomy use case, then followed by a distributed energy resource control use case, and then an advanced metering infrastructure use case. The last but not the least is a HPC-enabled transmission and distribution co-simulation use case. And we have some ongoing efforts to introduce as well. After that, we will have about 20 minutes of question or discussion. So first, let me briefly mention the history of this project. Before this project existed, we have multiple co-simulation projects that is sort of doing their own thing. For example, for this first project called Cyber Interconnect of DER, we have this kind of architecture. For the power grid side, we are using this open source simulator called GridLabD. And for the communication network, we're using this very well-known simulator called Network Simulator 3. And between them, we are using this grid modernization funded software, open source as well, called Helix, to pass the information between these 2 simulators. And but on top of those, we wanted a environment as realistic as possible, so realistic that we would like to run some source code in a virtual environment. So that's why we added a component called QEMU to and through a serial port. So in that case, you can actually put some of those binary softwares in QEMU. For example, here we actually put this OpenDMP3 protocol inside it, and also the fairly simple terms or DR binaries inside this QEMU, so that the NS3 only take care of the communication topology and the medium delays or packet dropping, but all the functionalities will be handled by QEMU. And this is a fairly heavyweight architecture compared to other projects, but you can see that here in red color, I highlighted all the developments we did specifically to this project. It's not a very simple approach because you have all these building blocks you need to develop. And then for another project, they may not be suitable anymore. For example, the other project called Robust Terms, we borrowed part of that previous architecture. But since this is a more lightweight project, we don't really need to emulate all those binaries in QEMU. We had to take off those. But to replace them, we had to develop terms and ER models as an NS3 application. So that's additional development. And that's, again, was done specifically to this project. And you can see this purple color here are all the new developments that basically I had to redo for this new project. And very often we, especially at the national labs, we would like to leverage our high performance computing infrastructure. So here comes another project that we actually is not entirely cyber physical, but we are doing transmission and distribution co-simulation. In this case, we would like to simulate different distribution networks in different computing nodes on a HPC cluster. So you can see again, we have many new development go into these coupling frameworks, and we have to enable HPC this job scheduler called Slurm, and have to write code according to that. Here you can see we are not using GridLabD this time. We use SIME to simulate the distribution grid. And for transmission grid, we use GridDyn, which GridDyn is open source, but SIME is a commercial software. We had to build on top of SIME a container so that it can be deployed to Linux system. If you don't know, SIME is actually only releasing Windows software. So it's only supported in Windows natively, but on top of that, we have to build a container so that we can leverage the HPC infrastructure, mainly in this Linux system. So with all this history, you probably realize there are a lot of lessons we learned from previous project. The first one is these models are really difficult to maintain. As you recall, for one project, we developed this QEMU instance, so the terms and DR models, they are deployed as binaries. But for another project, we have to write them as NS3 applications. And so essentially, models need to be redone multiple times, and it's difficult to manage and maintain them. And also, you see, we are using at least 4 different open source software, and they are constantly in their development and release cycles. Every half year, or even shorter than that, each software will have a major release. A lot of new features will be included. For example, for GridLabD, there were a big difference between 4.1 and later releases that the grid forming inverters are included in later releases. And if you are not constantly checking or keeping a track of all those compatibility issues, it could become really painful really quickly when you are trying to couple different softwares where they are releasing new releases every couple months. And the third pain point we identified is once you are doing these kind of simulation tasks, usually there will be domain knowledge blind spots. For example, I'm a power system engineer. I understand power system very well, but regarding cyber or communication network modeling, I don't know that much. But these kind of projects really require very well definition of responsibilities, and usually that will be involved into how you define those configurations between softwares, and those have been really challenging because everyone is only a domain expert, but they wouldn't dedicate too much time to learn another domain. The fourth challenge is that usually coming from an academic background, we usually just write Python or MATLAB or Julia. That's probably it. But for a lot of these DOE-funded projects, we will be building those open source software written in C++. And in general, that's itself is a very difficult software engineering task. Let alone we are building multiple open source softwares and have to make sure they build with each other as dependencies, and to figure that out is also very, very difficult. And the fifth one is, once you overcome all the four challenges, you are actually not done, because whatever model you develop, it will change based on the sponsor's needs or new studies needs. So you build certain functionality in your model, and maybe a few weeks later, you identify there will be new features needed for your new case studies. So your model is constantly evolving. Without a way to maintain those models, it's really difficult to reuse previous work or recycle your previous designs, because if every time you have to build the model from ground up, it's gonna take a long time for your project to even get to the interesting part of analysis. And the sixth one is somewhat related to why we take the time to put SIME into the HPC platform, is that when you are collaborating with utility partners, they have their own way of doing research or studies. So they prefer using a certain type of commercial software. And there are existing model format converting tools, but none of them are perfect. And usually if you would like to convince the industry that your study is meaningful, it would be more persuasive to use a commercial software. And there are a handful of them. Is difficult to switch between alternatives of those software. And the last one is that for different case studies, you have to configure the coupling between software in a very manual way before access. You have to pretty much write scripts to generate those connection points and make sure everything connects perfectly. And so that's the 7 pain points we learned from the previous experience with multiple co-simulation projects. And I will briefly talk about how we solve them across different use cases. And first, I think let's talk about this collaborative autonomy use case. A background of this use case is that it's trying to study a restoration problem. And this restoration problem is for distribution grid. And we would like to figure out a good way for using those renewable energy resources, or in a wider sense, using distributed energy resources as jumpstart units, and just from a bottom-up direction, restart the distribution grid and make sure the load and generation match, so that once they are reconnected to the transmission grid, they wouldn't introduce too much disturbance. And to do this kind of study, you have to model a distribution grid. Here we are using GridLabD. You also have to model the communication between those inverters. So in this case, we are removing a centralized controller. We are letting the inverters just talk among themselves and figure out whether their group of generation is sufficient to sustain the load that required to restart this portion of the grid. And then you have to model a communication network as well. And the challenges here is that in order to couple them in a meaningful sense, you can easily develop this communication topology through a routing table kind of inputs, or just assign IP address based on your preference. But for power grids, you have to respect the topology, the physical topology, and it is not that easy to automatically figure that out and link each node to their communication counterparts. So what we try to address in this use case is that we have a automatic way of figuring different levels of topology subgraphs for a power system, and therefore enable us to iteratively restore them from the edge of the grid towards a point of common coupling at the substation. What we did is define those seats as the location of the restoration units, and also you get a collection of the edge nodes of this entire grid. And some graph theory work is used here as well to remove those cycles in the distribution grid. Since distribution grid essentially is very radial, but there could be occasionally brief cycles, but removing them will facilitate easier translation of the hierarchy of the subgraphs. And the approach we follow is doing a search for lowest common ancestors for these portion of grids that you are interested in establishing as collaborative autonomy groups. So essentially, you can start from the very edge of the grid and having a lowest common ancestor as their first level PCC with switch attached to it. So once that grid's net load is communicated between inverters, and consensus is reached that they are okay to reconnect, they will reconnect through the PCC and re-establish a new collaborative autonomy group. And if you follow that route, after a few iterations, you will be merging all those subgraphs into one and reaching out to the substation, and hopefully connect back to the transmission grid without a large disturbance introduced. And so that's part of the configuration design for co-simulation. But when you go to each of these inverters, we have to enable some kind of collaborative autonomy feature in them. So in that sense, we don't want to do this work especially for this project. So we leverage this inheritance structure of C++ class. We first design so-called DOM devices. For here, it only takes its local measurements. And of course, all these devices are developed in NS3 as applications. For those DOM devices, they will do very simple tests, take local measurements, and send to any remote packet sync is defined to that component, and do nothing sophisticated. And for a smart device, we will be building a class as a child class from the base C++ DOM device class, so that you have certain local decision-making capability for this kind of class, but you can reuse all the measurement or sensing features from the DOM class, but adding new functionalities to make local decisions. We have build some application. As an example, it's like inverter learning application. It can leverage some history data and pretty much figure out the linear approximation locally. And on top of that, if you would like to enable the inverters to talk between each other, you can add new layers of functionalities called collaborative autonomy enabled features. In this sense, it will not only talk to the centralized, maybe a DMS system or DERM system, it will also talk among neighbor inverters and figuring out logic based on neighbors' information. So in this sense, we build this computation building blocks that is not only specific for a project, but it has a hierarchical structure that can be reused. If you are doing a simpler inverter control case, maybe you can just use a dumb inverter, or if you would like to have some local logic, you can use this smart inverter. But none of the efforts are wasted. You always can reuse them in this kind of design philosophy. And for this use case, we are doing this simulation in such a setup that we have some switch objects. For here, I'm showing a very small case here. You're trying to reconnect these nodes at the edge of the grid, and there are 3 inverters supporting the nodes. And the switch object does 2 things. First, it automatically query the switch status through a provided query cadence. We defined as 2 hours. And also it will listen to the DMS for a control command. So if the DMS tell the switch that our subnetwork is self-sustained and we want to reconnect to the rest of the distribution grid, then switch will take action accordingly. And then DMS is not directly making decisions by collecting all the information. It's actually collecting votes from inverters. And those inverters will just talk to their neighbors in a randomly triggered signs to figure out whether their net load is less than 0. That means they have sufficient generation. And of course, this net load estimation process can also be triggered by a predefined cadence. For here, just for the simplicity of this case, we only trigger it once at 12 p.m. That's when you see the load profile actually shows that net load is all their net loads are smaller than 0. That's when they reach consensus and send vote to DMS. The beauty of this approach is that the votes can also be compromised. So you can reach to a majority votes without everyone having to vote it. So if you have some adversary compromise one vote, if the other 2 is still good, you will still be making the correct decision. So that's set up this simulation. In terms of how the software is implemented, I can briefly talk about in this graph is that you have those DMS switch and inverter in S3. These are those communication specific aspect of those devices. For the physical representation, we are linking them to GridLabD through Helix publication and subscription features. So essentially, all the measurement or sensing information will be passed from GridLabD to NS3 through Helix through a publication, and all the command will be published to GridLabD, published to those mirroring objects in GridLabD through a command publication. In this sense, you tie these 2 simulators together to achieve this simulation. And for this previous mentioned small case, we are actually just doing a push sum algorithm. Essentially, every inverter will be able to pick a random neighbor to send its local net load. And once this net load estimation is initiated, they will start doing this kind of iterative process. And after certain iterations, all of them will reach to the convergence and send out votes. But you can see that since we are using this packet level simulation provided by NS3, we can track down how long it will take for inverters to converge. Here is roughly three seconds. And also you can also see the orders of packets being sent. And you also notice we put some buffer zone there is because we are doing iterations in a asynchronous manner. So not every iteration is synchronized with other components. So we put a safeguard there. There is some heuristic in there. So pretty much you see two of them reached the 10th iteration, but one of them only reached the 9th iteration. So, but since we put a buffer zone there, we make sure everyone will do some extra iterations, but making sure everyone will converge. And but that's good for a small case. We further increase number of inverters to 100, and this time you see this iteration process continues for a significantly longer time, 63 seconds. And but they didn't converge. If you look at the iteration, this bar chart here, some of those inverters have their initial message or initial estimation message queued up in their queue, but never sent. So that's something I think really justifies the co-simulation's value, is that you can have theoretically really strong algorithm, but when you have communication bandwidth limits, you have even, actually I can let you in of this secret. Here we are implementing the push sum algorithm a little bit differently. So some of them is initially the self iteration wasn't triggered. So it can actually help you identify some mistake you made in the algorithm, and also test the scalability of your algorithm with this platform. And a little bit of notes on this time consumed by this 100 meter inverters iteration is that it takes 63 seconds. It's probably still fine, given that your load profile in the distribution grid you wouldn't have too much change within 1 minute. But if you have a larger group of inverters, they need longer time to reach consensus, then is this method still valid? Or maybe you need to implement some improvement to reduce the time used by those iterations, because you're always chasing a moving target of the net load. If your iteration takes an hour, maybe at that time, once you reach consent for the net load of the previous hour, that is no longer the case. So there are a lot of considerations can be facilitated by this platform. Here, I just want to show, theoretically, this push sum algorithm works really good. You define those weight and self net load values, and the convergence theoretically can be reached with this logarithm complexity. So essentially, if you want to reach the convergence with probability 1 minus delta, for example, if you want to reach the conversion with probability 99%, and if you want to reduce the approximation error to 1%, and you're doing it for 100 inverters, theoretically, you need all inverters to reach their 6 iterations to reach convergence. But in real applications, you have network limitations, even the priority of how packets are sent, you may not always get such a nice convergence rate. So that motivates us to even study the traffic control method in AI3. Also, maybe instead of just a push sum algorithm, implement a push pull sum algorithm. In this case, for those inverters whose messages were never sent, they can actively initiate pull or protocol to get information into them. So all this is ongoing, and I think also it's a very good case to prove the co-simulation platform can show you some interdependencies that were hidden if you are doing individual simulations. And the second use case is a distributed energy resource control use case. There is not too much math in this use case. It's really that a software platform that step away further than just using simulators. We also have this virtual container QEMU talking to the serial port of AI3 application to simulate some attack scenarios for the grid. And this is published in these PS general meeting papers. You probably can see that presentation in a week also. And so essentially, similar structures are done using GridLab and AI3, but this time we are really just putting more emphasis on how the terms control those inverters and how an adversary could essentially make a malicious command or make a malicious firmware update to jeopardize the stability of the grid. In this case, we have actually four scenarios, but they are differentiated by two factors. Scenario one and scenario three, they all suffer a malicious command issued from the terms. But scenario 2 and 4 all suffers from a malicious software update issued from the terms. The difference between 1 and 3 and 2 and 4 is that whether the inverter physical delays are enabled in this case. The meaning of physical delay is that when you send a command to shut down an inverter, it usually doesn't shut down immediately. There is a time, depends on manufacturer, ranging from a few seconds to 1 minute or so to shut down. And also if you want to turn them back up, there is even a longer delay because they need to initialize the inverters. So in this case, the key takeaway is that for these kind of scenarios, if you have a collection of inverters with diverse physical delays, is actually gonna mitigate some effect of the attack because your inverters get shut down slower than immediately being shut down. So the recommendation from this study is if you are building an inverter or solar farm, try to use different manufacturers' inverters so that you are more robust in terms of those kind of adversary attacks. And we also developed some of those mitigation methods, mainly in this communication sense, not from the physical power grid sense. So for example, if we have a sort of a communication flow sniffer implemented in AI3, if you find out that command or update is from a address you do not recognize, you will deny that. Or if you accidentally accepted that, you will rewrite this command with historic records of the command. For the top two plots, the attack is issued without any these kind of communication safeguards. For the second one, we have the safeguards in place. So it received the firmware that is questionable, executed it, but then later, once the analysis is done, it will reload the previous valid firmware update to override this questionable one and bring the inverter back to operation. And there are a few other use cases. For example, if the attacking adversary is kind of playing with your inverters, turning them on and off, we also implemented a mechanism to identify that and mitigate that. But this time, the mitigation can be categorized as corrective and preventative. For preventive actions, once it's identified, the inverter or the terms will act in a conservative way, because in order to mitigate the oscillations, it would just rather not having those inverters generating any power. But for the corrective mitigation, it will actually take some more time. You see here, the corrective mitigation actually take longer time to take effect. Take some more time to analyze how the inverters are behaving in an abnormal manner, and but then it will be able to reverse these changes and bring it back to normal. So in this time, you suffer oscillation for 6 minutes, but then you have the inverters back to normal working again. But in the previous corrective action, in the previous preventative mitigation, you don't tolerate any oscillation. You started oscillating for 2 seconds and you bring everything down. So it depends on the priority of operation. You could be prioritizing the safety, so that you act more conservatively, or you could be prioritizing the generation. So you will take some risk, but make sure inverters will be generating again. So that's the use case for this ER control. And the third one is an advanced meter infrastructure simulation use case. And in this use case, we actually swapped GridLabD, an open source software, with Sign. In this case, we have a really large meter network modeled in NS3. There are cell relays and there are meters, there are routing tables defined in NS3 as well. But this time we attach each meter to their Sign model counterparts. And in that case, the electricity usage reading will be passed to these meters. And in this case, we want to study the interdependency between different reading scenarios, because for this specific partner we are working for, there are at least 8 different scenarios. You could just read electricity usage, but they also can read voltage reading as well, just to prepare for any security mitigation strategy. So the traffic in S3 could change depending on your reading scenario selection. And we just built this platform to simulate some scenarios to probably provide a bottom line solution for this partner, that what if you have something going on in terms of jeopardizing the security of your power grid, and then also your communication network is flooded, how those will affect your next investment. Should you improve your communication network infrastructure, or you should invest in those automatic protection schemes in your power grid? This is another ongoing project. And so the last one, not entirely on topic for this seminar, but I really want to introduce it a little bit. It's really nice, is coupling the transmission grid and with distribution grid. We have a paper accepted by the SGD Europe conference this year. In this case, we have the transmission grid simulated on one node in the HPC cluster, and we have another 100 distribution simulated in a distributed manner on different nodes of the cluster. And essentially, we do a time series study of a given duration of the time, and simulate how much speed up we could achieve by doing this. The results are pretty promising. You can see that in these speed up plots, we have a substantial part represented by green, which is how much time was taken by each computing node to initialize the SIME container environment. In this case, SIME is built into a container called Duan, and then stick that container into Linux system, use the job scheduler Slurm to start them. That takes some time. And also between each snapshots of this time series, you have the communication between, you have this information exchange between transmission grid and distribution grid. That also takes some time because you actually need to talk to different nodes in this computing cluster. That's this darker blue portion of time consumption. And then you have all those power flow solution time represented by red. We are simulating a 30-day time series here. But in this case, you're only limited by the longest time consumption. So for this case, we were able to achieve 72 times speed up comparing to simulating everything in one node in a serial manner. And another additional case is that we could apply the same methodology to the integration capacity analysis on HPC. In this case, we are deploying different PV installation configurations at different computing nodes and simulate them in parallel. And we could pretty much done this screening of about 50,000 HPs, 50,000 PV installation scenarios, and achieve pretty much get it done in about 1,400 seconds, and identify what are the scenarios that is acceptable and what aren't acceptable scenarios. So this will really speed up the integration capacity analysis use operation task for the utility, and that's pretty much is what we have done. And here I would like to briefly mention about this direction we are going into. As I mentioned, building open source software is really painful, and we are developing this flat solution called Access Core, which will act very similar to a package manager in other languages. For example, if you have used pip install, or if you on Linux you have used apt-get, or this kind of package manager, this is very useful when you are juggling different release versions of softwares and different dependencies. We leverage this tool also built at Lawrence Livermore called Spec. It's pretty much a collection of all the open source dependencies, especially with an HPC emphasis. This kind of package manager, we use that to integrate our simulators together. And when there is a new release coming out, we can easily swap that with the previous one. So the syntax here is, if you do a spec install GridLabD with the feature, with the Helix feature, using the compiler GCC 9.2.0, you can just do it in a line, simply like this. And Helix spec, they call it recipe. So how you cook up a Helix software. This recipe is maintained by us, Lawrence Livermore. IS3 recipe is maintained by the IS3 developers. GridLabD recipe is maintained by us and PNL. So whenever there's new release, we'll update the recipe, and you can fairly, in a painless way, to get all the software built together and making the dependencies correct and get a running example to validate whether your software is working correctly in together. And I mentioned you can run a very small example. That's also something we are including to the access core. Very often, when you are building one software, you have all those unit tests that you can run through to double check whether your software is built correctly. But you are building multiple software here. We actually developed this kind of minimum example to help you double check if you build GridID with Helix feature, whether they are built correctly. So that's taking all the experience we have with all this development, concentrate them into a minimum example, and making sure if this runs correctly, all these switch control, weather forecast, meter reading, inverter control, flexible load features will be available for you. So that's something ongoing. Not the recipes are released, but the source code, we haven't really put it on schedule yet. So that probably wraps up my presentation. And I think I'm a little bit over time, but we have eight minutes.
Yes, thank you, Nan. Yeah, we have a few minutes for questions. I have edited the security option, so anybody can unmute themselves and ask questions, or you can send your questions in the chat. And I have one question first I would like to ask is coming from Sigi Bu from Hong Kong Polytechnic. Can you please comment on the interactions between transmission distribution which are observed during co-simulation?
Yes. So for transmission and distribution co-simulation, I would say that I actually didn't dig into detail of how the algorithms, the power flows are coupled together. In that sense, it's still a very open research area. We were focusing on the improvement of speed, but in terms of coupling them, we are pretty much using a fixed point iteration type of approach. You pass the voltage from the substation to the feeder, and you pass your aggregated load value PQ back to the transmission, and doing iterations in that sense. We have encountered cases that if you have those regulators in distribution grid enabled, you will have jumps in power flow, and it has suffered difficulty in convergence. But I guess, yeah, that's still ongoing in terms of research. There are new projects going on I'm aware of doing that kind of algorithm study.
Thank you. Any other questions from the audience? You can unmute yourself and ask the question.
Yes, this is Jim Strite. Thank you, Nan. I have a question about power line communications. That power line communications uses power systems themselves as a communication medium. Now, is this sort of communication considered part of the communication network, or is it part of the physical grid itself?
Actually, we haven't done that kind of implementation. I believe that would more fall into the transmission side. And if we were doing that kind of case, we probably would have a communication counterpart for those. Yeah, but we haven't done anything regarding that yet.
Okay, and I have a somewhat more a deeper question concerning the task force itself. On the task force website, under the task force motivation and scope, are the following words. It says, the future smart grid is extending its functionality by allowing a two-way flow of both electricity.
Jim, let me interrupt you there to focus on your questions of the presentation, and we can talk a little bit about the task force later on, because we don't have much time for the audience.
Okay.
If that's okay.
Yeah.
And with that, I have one question that is coming from the audience. And can you comment on the protocols that your platform supports in order to monitor and control the DR devices, the inverters in the co-simulation? Do you support, for example, Sunspec Modbus, IEEE 2030.5? What are the protocols that you're supporting?
Yeah, so the protocols, pretty much everything available in S3, we can use them. And we are developing this Modbus implementation in S3. Is ongoing this summer. We probably will submit a pull request to S3 developers to get that Modbus development merged. But yeah, that's started from a previous project and carried over to recently, and we are wrapping up some Modbus development. And other than that, anything available in S3, actually DMP3 is not available. That's why we stick into a QEMU instances. So yeah, DMP3 has to use the virtual environment. Modbus, we have a native S3 implementation almost there.
I see. Okay, and I have a follow-up question actually myself about this. Is there any reason why NS3 was selected? Are there were any specific properties you were looking for? I mean, there are other open source network emulators that could be used for this co-simulation. For example, the simulation step is important, or any other properties that you were looking when you selected NS3 as a network co-simulation environment?
So mainly this is just really popular at our lab and also you can write application in C++. That's sort of give us the flexibility to define different applications with different features and reusable. But other than I'm aware of a lot of other network simulators, but we haven't looked too much into them.
Okay, thank you. Any other questions from the audience? We have 2 more minutes.
I have a question. Can you hear me?
Name and affiliation, please. Yes.
Yes, I'm Yannis Zographopoulos from Florida State University. So regarding the inverters attack scenario that you mentioned in your co-simulation, you only talked about firmware updates and shutting them down on or off, and what are the results of this type of behavior. Have you also looked into the stability of the system if, for example, the inverters are maliciously controlled and you are injecting power, reactive or active power to the system?
Right, for this project, we were more on the communication side, but there is ongoing project I talked about, it's called robust terms. It's actually taking the power system measurements and figure out whether the command would jeopardize the security of power system. So yeah, this project will address some of the issue, but I didn't include it in this presentation. For the cyber interconnect project, we are more thinking things from the communication modeling side.
Okay, thank you.
Sure.
Thank you, Nan. Any other question? Is 2 p.m. EST. I think we are perfect on timing. If you have any other questions, you can redirect them directly to the speaker. And with that, I would like to thank everyone that participated today in this webinar. We'll send an update for the upcoming webinar in the next following days. And again, thank you, Nan, for the interesting presentation. And thank you everyone who participated. We'll post the presentation of this webinar on the website. So please subscribe to the membership list so you can follow up and get all the details about the task force. Thank you again, Nan, and thank you everyone.
Thank you,
Thank you, everyone.
Thank you everyone for attending.
Bye.